algorithm. Yeah. So basically, so for those functions, so those will become our kind of the central problems to kind of study in algorithms in general. Okay. So that doesn't mean that these are the, I mean, only things to study or something like that, or this is the only best way to study. But this is a very generic approach of studying algorithms. So that is what we will be doing today, and you might have already seen some of this kind of stuff before. For example, in your discrete math course, you must have seen how we can use graph theory to model various problems in various problems, right? Various discrete math problems. Or similarly, we have seen how to maybe use say DFS, BFS kind of stuff to answer some of the questions. So today also we will be doing talking about a similar kind of a problem. So let me start here. Can you see my screen share?
Yes, sir.
So let me start with actually presenting a problem. Okay. Okay, so not presenting problem. So today we will be talking about what is called optimization problems. Okay. So optimization problems are a very generic class of problems. You have already seen some of it, or some of them. The main idea is that you have been given an input and you have to find a structure from the input that optimizes something, or find a solution that optimizes something. So for example, you have seen the thing of shortest path, right? You have been given a weighted graph and the goal is to find the shortest path between S. Or you have been given a knapsack instance and the goal is to find a solution so that you can take the maximum amount of element in your stack, maximum cost of element in your stack. So there are some other examples. I mean, I have given some examples which are more from the point of view of machine learning and artificial intelligence, which people are so fond of usually nowadays. So the simple optimization clustering problems are nothing but optimization problems. So maybe can one of you kind of give me a problem that is not an optimization problem? Anybody that you have done in the class at least? Surajit, are you there?
Yes, sir.
Yeah. So did you understand what is an optimization problem is?
Yes, sir.
Can you tell me of a problem that you have done in this algorithms course till now, which is not an optimization problem?
Sir, sorting problems.
Sorting, very good. Sorting is one of them. So you have been given a unsorted list and your job is to sort it. There is nothing that you want to optimize, right? So that's an example of a problem which is not an optimization problem. So hopefully you will understand the whole concept of the optimization problems. And the optimization problems are, of course, one of the most commonly used problems in real life as well as in algorithms. So let's start with one such problem. Okay, here is a problem. Okay. So there is a factory, and in which they want to transport goods from one place to the another, right? And they have got 3 wagons on which they have to load their material and ship it off to the other side or something. Okay, and now they have some, of course, each of the wagons have some constraint. So they have a constraint.
Sir?
Yeah.
Can the sorting problems can be made into optimization problems?
How?
It can be, right?
No, I mean they
like say I can assign some weight function whether like say AI and AI plus 1 if AA plus 1 is less than or equal to AA plus 1, then I'll say that I'll assign weight 1 to it, otherwise I'll assign weight minus 1 to it. So it is like finding maximum positive value assigned to the given sequence.
I don't understand this thing, but see, I mean, okay, maybe
It's
you
like
can look
inversions,
at it.
inversions in permutations.
Okay, you can do something, okay, but usually sorting algorithm is not an optimization problem. I mean, nobody thinks of sorting algorithm as an optimization problem. Okay. You can
Okay.
possibly formulate a sorting algorithm in a very complicated optimization problem setting. That also I'm not 100% sure how you do that, but that is not exactly what people usually think of it. Okay.
Okay.
I mean, of course. I mean, so again, these classifications are not necessarily always. I mean, it's not like something is an optimization problem doesn't mean that something is not an optimization problem and so on. But
Yeah.
The main idea is that okay, so optimization problem is something where you try to optimize something. Okay, optimize a parameter. Fine. So here is this one of the optimization problems. Okay. So you have this three wagons, and each of them has some upper bound on the amount of capacity in terms of the weight, as well as the capacity in terms of the volume that they can handle. Okay. And they have here some certain set of cargoes, and the job is that okay, he can send these cargoes in various parts. I mean, there's the one kind of cargo that are very heavy and the volume is not that much. But if we can actually ship this cargo C1, then he will get a profit of 2000 say rupees or 2000 I don't know, something unit of money per ton. Okay. Similarly, C2, C3, and C4. Now the goal is that how much cargo will this company be able to ship using the three wagons, and how much and which wagons should contain which kind of cargo, and so on and so forth. Is this problem clear? Hello? Because it is important that you understand these problems and think about these problems. I will give you 5 problems. I will start with giving you 5 problems one by one, and then slowly show you how they can all be solved using a similar approach.
Sir, for loading the wagons, we are using one among the 4 cargoes.
No, each wagon can contain, say, some tons, say some tons of C1, and it can have 2 tons of C1, 3 tons of C2, 1 ton of C3, and no tons of C4.
Okay.
Okay, a wagon can carry all of those kind of small parts. So think of these cargoes to be, say, maybe, I don't know, some iron ore and coal and whatever stuff. So it's like you can split it up into small tons.
Oh, so these cargoes are the materials that are to be finally loaded into our wagons.
Exactly.
Sir,
Okay.
then C4 will not be loaded in any of the wagons, right?
Yeah, maybe.
Okay.
Maybe. No, that is also not true. Hold on.
Because available ton is 20.
Yes, but you don't have to send 20 tons only.
But in wagon 1, it is 10.
Yes, I can send
capacity.
send just 10 tons of this C4.
Okay.
I don't need to send, when I am sending a cargo, I don't need to send the whole amount of available ton.
Okay.
I am allowed to send a small fraction of the available ton. Okay, so of course you cannot load the total weightage in terms of ton of all the cargoes that goes into W1, that cannot be more than 10 tons. Similarly, total weightage of the various cargoes that go into wagon 2, that cannot be more than 8 tons, and so on. And on the same way, I mean, there are some cargo can take a lot of space and some cargo less space, right? So if you are packing, say, 10 ton of cargo 1, right, into weight into wagon 1, then the total volume that it has already eaten up is 4,000, right? 10 into 400 is 4,000, and the profit that you can get from this by sending this W1 is basically 10 into 2,000. But since the wagon 1 has already reached a capacity of 10 in that case you cannot send anything else. But maybe that is not the most optimum thing to do. Maybe you can send something else. Maybe you can send
C3,
say C3 maybe.
because its profit is more.
Yeah, fine. Yeah, exactly. So it might be the C3 might be the right way to send. Okay, but C3 also has a problem that it has only very few number of tons, right? So this 5, so do you send the C3 all the 5 tons into one shot, into one wagon, and in that case in which wagon? And the other one is that if you and
Yes.
or should we break it up into small parts into these 3 different wagons? Hello.
Sir, first we can send C4, sorry, C3, like, you know, if any of the wagon is chosen, because it will maximize our profit and it will take volume
No, what
less.
when any of the wagons is chosen? You have to tell me the C3, how much will you send in which place? Right? Do you send 5 tons of C3 in wagon 1, or 5 tons of C3 in wagon 2, or 5 tons of C3 in wagon 3? Or should you spend maybe 1 ton of C3 in wagon 2 and 2 tons in wagon 1 and 2 tons in wagon 3? Right? So you have to give me an allocation. You understand the problem?
Yes, sir.
Yeah. So of course, see again, a normal person who doesn't understand algorithm possibly will try to solve it by trying to use some very clever idea that, oh, so let's do this one, let's do that thing, and so on, and maybe this will help, right? But you guys are no algorithms, and that is where it should come in. That why don't I, instead of trying to use my brain to solve this one for this particular instance, write an algorithm to solve it? Okay, and that's exactly what we will do. So is this problem clear to everybody? Hello.
Yes, sir.
Very good. So if it is clear, so let me go to the next problem. I'll first explain the 5 problems that are there, and they will be a different kind of 5 problems. Okay. The next problem is, this is called a bang for buck in advertisement, right? So basically, I mean, so say you have an advertisement company, you have been hired in an advertisement company, and you have been given that, okay, fine. See, you have been given 6 crore rupees to come up with advertisements. Okay, and you have only 10 people who can handle in your team, right? Now your job is to kind of decide how to spend your money and your team members, or allocate your team members to various things. So maybe what you can do is that you can say, okay, fine, can I ask, maybe I'll find out the Cricket World Cup, and to put the advertisement in the Cricket World Cup, I will need 3.45 crores, and I would expect to reach 10 crore people. So that is the number of people who will be watching our advertisement. This is, I can hope. But for that, I will need 5 people of my 10 people to handle this whole thing. Or I can decide to go for IPL, and I can go for, I can spend 5.2 crore, and in which case I can try to reach to 15 crore people, a lot more people, but also I will need a lot more of my people to work in that project. So maybe after I decide which one to go for, I can also, if I with very small amount of money, I can 0.1 crore, I can go to the radio ads in, and total number of people I reach is very small, but I will need 3 people, and so on and so forth, right? So you have been given 6 crore and told them go and spend as much as you want, or as in whatever way you want, and you have been given 10 people in your team. Now your job is to decide how to, which all places you can invest. Can you invest in World Cup? Can you invest in IPL? Can you invest in radio? And so on and so forth. But in every place, you know that, okay, if I decide to invest in Cricket World Cup and radio and so maybe and TV ads of the non-peak hour or of the peak hours, say, then the total amount of money that I will need is 3.5 crore plus 0.1 crore plus 1.5 crore, and that is 5.1 crore. Oh, excellent. So that is within my budget. Very good. In that case, I managed to reach 10 crore people plus 0.5 crore people plus 4 crore people, which is 14.5 crore people I will able to reach. But to execute my plan, I would need 10, 5 plus 3 plus 4, which is 12 people. Oh, God, I don't have 12 people in mind. So that's not a feasible option, right? So so you have to come up with various strategies about which is the best way of utilizing your money. Again, is this problem clear?
Yes, sir.
Excellent. Yeah, if any one of you are not following this problem, just do let me know. I will repeat them one after again and again. So third problem is a very simple problem closer to home. So there are n MTech students, S1 to SN, and in ISI, and there are M faculties, F1 to FN, and each student submits a list of faculties with whom he or she wants to do the thesis. At the same time, this faculty also submits a list of students with whom he or she will be happy to supervise for the master's thesis. But on top of that, each faculty says that, oh, I mean, I cannot. So one faculty says that I cannot handle more than one PhD, one master's. Another faculty student might say that I cannot handle more than 3 master's students, and so on and so forth, right? And now your job and your is that, is it possible to come up with an allocation of this assignment of students to faculties such that everybody's wishes are maintained? Meaning, if an S1, if a MTech student S1 is assigned to faculty FM, then it should be that S1 was interested in working with F1, FM was interested in working with S1, and the total number of students that FM finally gets to is assigned to is less than the number of students that faculty was ready to take. Again, see, these are very, very real life problems, many things that are faced day to day in various contexts. Okay. Is this clear again? This problem?
Sir, does the list is in terms of order of preference?
No, there's no order of preference.
Okay.
There's no order of preference or any such things. Okay, this is just a list.
Okay, sir. Fine.
Okay, and your job is to find out whether there exists one or not. Fine. Okay, so here there is another one, the telephone towers. Okay, so there are certain spots in the city that the telephone company wants to ensure that these are the spots in which my 5G network must be very good, very strong. But to ensure that that company has to upgrade the towers at certain locations. Of course, that company doesn't want to upgrade too many towers, because upgrading a tower costs money, right? So what the company realizes is that if from any point there is a tower within 1 kilometer radius, then that's good enough. So if I put a tower from in the 1 kilometer radius of that tower, there are 5 of these important locations. All the 5 locations will get very good 5G, right? And so on. Now the company's job is to decide which all places the towers should be upgraded, so that the total cost is minimized. The total number of towers that has to be upgraded will be minimized, and at the same time, all the important locations in the city are covered with the good 5G network. Is this problem clear, Ken? Hello.
Sir,
Yeah.
Sir,
the location should be like
Location should be.
there is no mention of the locations.
Of course, there are some upgrading, right? So there are certain towers in certain locations. Those are the places where you will upgrade the towers. Right? So certain towers are already there. We are not talking about putting up a new tower. Yeah. So you basically have a certain set of locations where there are towers already, and certain set of locations in the city which you want to serve. Now your job is to upgrade some of the towers so that you can have good 5G coverage in all the important locations. Yeah. Somebody
Yes.
else also wanted to ask something.
is this anywhere related to vertex covering problem?
Yeah, I mean we'll see about it.
Minimum vertex cover.
Yeah, you can think about it. Okay, all of them we are talking about are of course related to something.
Okay.
And any other questions of this particular problem? Okay, so if not, I think I have one more questions. Oh, okay. This is something that you might have already seen in your assignment actually. So it's called the scheduling problem, and there are and you are supposed to schedule meetings. Okay, and various meetings. So say you have joined as a company in a company, and you have been told that okay, see there are these 6 meetings that has to be held. Okay, and for each of the meetings, M1 to M6, they have a start time and there is an end time. Of course, 2 meetings which have time at any point of time in a particular room, 2 meetings cannot be held, right? It has to be only 1 meeting, and you have to find out what is the minimum number of rooms that you need to book so that all the meetings can be assigned. Okay. So these are the problems. All of them are kind of optimization problems. And the main idea is that they're all kind of problems picked up from kind of a real life instances. And this shows that, okay, so these are if you join a company after you finish your masters and all, you will be facing such kind of questions. Okay. I mean, such kind of questions, meaning questions that are not of the form that oh, here is a graph and do something, or here is something, or here is something, sort it. No, the problems are kind of a real life problems, and your job is to solve them. Okay. Now, how do you solve them? And this is where the most important things come in. Okay. So, as one of one of your friends, Shiva, I think, was pointing out that one of the problems do look like a graph problem. And and that is actually correct. Many of the problems can be written as a graph problem. Okay. And you can see that this graph problem can be used to model some of the problems. Okay. And that is also the reason why we study certain graph problems. Okay, certain graph theory. We study graph theory. Right. But then also there is this issue that graph theory is a beautiful subject. You can design lots of questions in terms of graphs. But when it comes down to algorithms, do I have to come up with a different algorithm for all different graph problems? Or are there some way of handling them in one go? Right? Now, again, this also you have seen to some level, right? You have seen some special cases, some special structures like connectivity and so on, or shortest path. And so these are the cases where you can say that, okay, see, these are if you can reduce to one of these problems that we have known, then that's good. Okay. But again, the same question can be asked. So you have to you have to be very ingenious then, right? For which problem, which graph algorithm can be reduced to which one? You have to find out and come up with some ideas. And there is of course an infinite collection of graph problems. So I mean, that's not an easy job, right? And that is not how people work in the industry. Okay, so I am going to give you a very nice trade secret in this whole in this week. Okay, I will start with, I will not go into graphs for now. I will go into the problem of something else, modeling this set of problems using a different way that you have not seen till now. Okay, I will spend today's class, rest of the class, on that particular way of writing, basically using what is called a linear programming.
Yeah.
And the next class we will be seeing how we can use some other graph structures and something else called SATs, or satisfiability problems, to model problems. And let's see, let's go ahead. Okay, so the common approach that we are going to talk today is what is called linear programming. So linear programming is something that you have done in your high school, in your life, in actually speaking. Okay, so what is it that we want to do? So you have been given a linear equation. Okay, 3x plus 4y minus 10z. Okay, and you have to come up with an assignment of x, y, and z that maximizes this quantity. Okay, simple enough till now. But you also have to satisfy some constraints. Say there are these conditions, right? For example, 5x plus 8y is less than 15, and x plus 5y plus 2z is less than 10, and something is more than 4, and x and y must be numbers that are between 0 and 1, and z is a number that must be positive. So under this set of constraints, okay, can you maximize this quantity? Okay, what is the maximum value this quantity can take? So this kind of programs is what is called a linear program. Okay. Now, why linear? It is linear because everything is linear. All the thing that you are optimizing, maximum, or it can be max or mean, doesn't matter, right? This is a linear quantity, and all these constraints are also linear. They're linear equations. I leave it to you guys to think about how you can formulate it as a general math problem. I mean, it's pretty easy. I don't think I have the thing written up over here, but basic idea is that this maximization is nothing but this whatever is there, or this basically any equation can be written as a dot product of two vectors, where one of the vectors is the vector x, y, and z. Right? And this set of constraints, all of them can be written as a dot product of a matrix with that variable vector is less than some quantity. So I will not go into that thorough details over here. Okay. But this problem, it looks like a very simple problem, right? Have you guys seen this problem before?
Yes. Sir, why can't we use some differential calculus techniques here? Like,
I mean, what do you want to do?
like given this function maximum of fx under this side chain conditions.
I mean, are you trying to solve this problem?
Yeah, trying to solve the problem.
Yes, okay. Yeah, I mean, there are ways of solving it using that thing, using various kind of techniques. I will come to that. I have not even talked about the kind of solution for this problem. I'm just talking about this problem as a whole, okay, where you are maximizing or minimizing a linear constraint, a linear equation under the constraints, under certain set of linear constraints on the equation, on the variables.
Okay.
Is it fine? This
Yeah.
how many of you have seen this seen linear programming before? Can you please raise your arm and or in your the Zoom chat?
Yes, sir, we done our graduate course. There is linear programming course. One course,
Which course?
operational research course.
You have done operational research in your MTech?
No, in our graduation we done this.
Sorry?
In our
What is
graduation, we
graduation,
done this.
undergrad or graduation?
Undergraduate.
Okay, good. Okay, so there are few people who have seen it, but not many people have, or the rest, many of you have not seen it. So it's good that we are doing it. But I can also promise you that everybody of here has seen some version of this one. Can you guys say which one is it? I'm saying you have seen it in your high school.
Solving linear equations.
Exactly. Solving multiple linear equations. That is actually what you were doing that time, was actually a linear programming of a special kind. Okay, simultaneous linear equation. And that is exactly how even this particular problem can be solved. Okay, so let me just say here. Okay, so the very important factor that has been that is important is that what are these x, y, z? Now, this is something that I will come back to very soon. Where we can assume that x, y, z are real numbers. Okay, a real number, then that is important, very important. So this is what is called linear programming. And there are some very nice packages in any programming language that you can think of. So for example, here R is a language package that deals with statistical works and all, and they have this package called LP-solve. Okay, then there are every possible language has this very nice package to solve LP for linear programs. Okay, and So it is kind of important that if I can model my problem as a linear programming problem, if I model my optimization problem as a linear programming problem, then I'm game over, I'm done, right? Very simple.
Sir, in this case, X, Y, Z are real numbers,
Yes.
but is it like always that's not means
no,
problem-wise it will vary?
Yes,
Okay.
yes. When it, yeah, so yeah, X, Y is the real number. Yeah. So okay, so I can skip this one. So this is how basically you end up inputting this kind of a linear programming into a into one of the packages kind of stuff. But the important thing is that, okay, so linear programming is a very, very well studied problem. Very, very, very well studied problem. I mean, this is a problem that has its roots back in the Middle Ages, and in terms of this algorithmic concepts and all, it has been really well thought out, solved, and we are now we can now even go beyond linear programming, and we can work with what you can call quadratic programming or higher level programming. So even those are there are nice packages and all that can handle many of those kind of stuff. They're not called quadratic programming, they are called semi-definite programming, but I'm not going to go into all of that. If you are interested, regularly there are courses of optimization that are given in ISI. Feel free to take them, and they will have a more thorough study of this linear programming problem, how to solve them and so on. But the most important part here is that if the variables are guaranteed to be reals, okay, you are allowed to put the variables x, y, z in any real numbers that you want. I mean, so basically their range is the real numbers, and all you have to do is just satisfy those constraints and maximize that quantity. Then this problem can be solved in polynomial time. Okay. Now, this algorithm for solving this problem, it's not easy. Let me put it this way. I mean, it was first solved in the 1960s, and then in 1975, a new algorithm was proposed, and in 1981, an Indian came up with a different algorithm, and they are all studied in the optimization course. Every possible such algorithms are looked into with very good depth, and so on and so forth. But for this course and for most of your work, you don't need to know any of those algorithms, because what we are talking about is not how to solve linear programming. Because linear programming, if I can guarantee you that the variables can be in real numbers, then there are packages that just solves it in, I mean, they are very fast in solving these linear programs. Okay, theoretically, they can be done in polynomial time, and they have been implemented. Okay, and this is where what I'm trying to say in this particular lecture, that the job is not to solve linear program, but the job for an algorithm person is to reduce a problem or model a problem as a linear programming problem. And that's it. After that, we have packages to solve it. Okay. And yeah, so there are very nice libraries that are there that can solve this linear program. And the trick is in the modeling the problems in the LP form. That's it. So this thing of modeling is something we call reduction also. Okay, we reduce one problem to the another. So if I can model one particular problem to LP in an LP formulation, then I say that I reduce that problem to LP. So let's start with this simple one. Do you guys want to go for take a shot at how to write an LP formulation of this problem?
Sir, I have a doubt. Like,
Yeah.
when can given a function and site conditions,
Hmm.
when can it have a optimization solution? Like, what about whatever the object polyhedron forming using that side chain, and
If the
if it is open?
constraints are linear, okay, if the constraints are linear and
Does it
and
have
the
to be bounded?
optimization thing is also linear, okay, and the values and the variables are allowed to be reals, in that case it can happen only two things. One, there is no solution. I mean, there is no solution that satisfies all these equations and so on, all these constraints. Or two, there is a solution to all the constraints that satisfies all the constraints, and you will have the optimization result, and that optimization result can be found in polytype.
Okay.
Okay.
So no solution as in like maximum or minimum can't be found.
No,
Like
it's not a maximum or minimum. The constraints are different. So if I say that, okay, fine, give me an x, y, and z such that x plus y is less than 1 and 2x plus 2y is more than 8.
Yeah.
Can you do that?
No.
No, correct? Why not?
I mean, not even okay.
Because these two constraints are contradicting.
Yeah.
X plus y is less than 1. And the other one is that 2x plus 2y is more than 8. That means x plus y is more than 4. I mean, you cannot give me an x and y that satisfies both of them, right?
Yeah.
Right. So it is possible that if you give constraints, then there might be cases when there is no solution. Okay, what it means that there is no solution that satisfies all the constraints.
Yeah, like given that the constraint satisfies, I mean, there are solutions. The solution set of the
Yes, and then there exists a minimum and a maximum. I mean, okay.
Minimum or maximum.
Yeah, so let's not go into that whole thing. Okay.
Okay, fine.
Yeah, so there are issues about boundedness, non-boundedness, and lots of kind of stuff up there. Okay. Again, I don't want to go into this. I don't want to make this class into an optimization class.
Okay, fine, sir.
Okay, the goal is not to talk about the LP solutions and all, but how to model a problem in LP.
Okay, sir.
Yeah, so if you are interested, I will certainly encourage you to take the optimization course. Okay.
Yeah, sure. I mean, I'm looking for some convex polyhedron or something like that, but yeah, it's fine.
Since the things are linear, since all the constraints are linear, it's a convex body.
Yeah.
Okay, so that helps you in understanding.
Like if it is open or not, yeah. Like if it is open,
Yeah,
something
again,
can't be achieved.
let's not go into it. So, by the way, did you guys manage to? How many of you actually managed to write this one as a LP problem? Only one. Okay, let's see. What about the rest? So the main trick of writing an LP thing is to come up with the right definitions of or right variables. Okay. So here, for example, I can say that okay, x1 is the amount of ton of the cargo C1 that is loaded in W1. Y1 is the amount of ton of cargo C1 that is loaded in W2, and so on and so forth. So by the way, I have just kind of shortened my problem. I think initial problem there were three wagons, if I'm not wrong, but I've just shortened it for explanation, simplicity of explanation. Okay, so right now I have just 2 wagons and 3 cargos. Okay, and that's it. But you'll understand the whole idea. So I have 2 into 3, which is 6. So I can write 6 different variables: x1, x2, x3, and y1, y2, y3. x1, x2, x3 is basically the amount of cargo, amount of quantity of cargo 1, cargo 2, and cargo 3 that are loaded in this one. Yeah. Yeah, speaking. Hello, sorry. Yeah. So we have this x1, x2, x3 are the quantity of cargo C1, C2, and C3 that are loaded in x1, a cargo wagon 1, and y1, y2, y3 are the amount of cargoes loaded in wagon 2. And now see, you can write this whole thing very easily, right? What is it that we have to guarantee? First of all, let's write the weight constraints, right? Okay, so what do we want to optimize? Okay, what do we want to optimize? So if I send that x1 quantity and y1 quantity of C1, then I am sending x1 plus y1 quantity of C1, and the total profit is 2000, right? So 2000 into x1 plus y1. Similarly, 2500 times x2 plus y2. Similarly, 5000 plus x3 plus y3. So this will be the total profit, and this is what we want to maximize. And what are the conditions? First of all, the condition is that each cargo, there is a maximum limit that I can send, right? So x1 plus y1 must be less than 18 ton. x2 plus y2 must be less than 10 ton. And x3 plus y3 must be less than 5 ton. Excellent. The next one, okay, the amount of quantity that goes into in terms of weight in the wagon 1 must be less than 10. So x1 plus x2 plus x3 is less than 10. And similarly for wagon 2, y1 plus y2 plus y3 must be less than 8. Right? Now third is the space constraint. So if I'm sending x1 ton, the volume required is x1 times 400, right? If I'm taking x2 quantity, then the volume required is 300 times x2, and volume for x3 I need 200 times x3, and this whole volume must be less than this 5000. And similarly for wagon 2. And that's it. All I need is that x1, x2, x3 and y1, y2, y3 are greater than 0. Right? And see that they are completely, so this gives this as a linear program.
Sir, here x1, x2, x3, y1, y2, y3 are integers.
They need not be integers, right? That's what I told. I'm told it in terms of the IRA node, and also it doesn't have to be integers.
Achha.
Technically, I can send it for anything, right? Okay, so this is the linear programming formulation of this problem. And you solve it, and you can solve it using this nice LP solvers. Done. Okay. So let's move to the next problem. A similar. So again, these are the examples where we need to kind of get our hands kind of working. Okay. You remember this bang for buck in advertisement? So let me give you another couple of minutes. Why don't you guys try to think about LP formulation of this whole thing? If you are done, just raise your hand. So nobody could get it done. Aditya? Luna got it.
Yes, sir.
Yeah, so you are the person who did it last time quickly. This time
Yes,
you could
sir.
not do it? Or you didn't try?
Sir, this one I'm not able to understand which thing to maximize.
Which thing to
Oh.
maximize? You want to maximize the number of people you want to reach.
Okay. Yes, sir.
Okay, good. So there are a couple of people who managed to get it. So let's see. So now let's try to do. Okay. So now issue is a bit interesting. Okay. So I can decide. Okay. So there are these 6 possible options, right? X1, X2, X3 to X5. 5 position, 6 position. Okay, whatever, 5 or 6, whatever options, right? And I want to kind of attribute a 0, 1 variable indicating whether I want to invest in that particular form of advertisement or not. Now note that I could not have told that, okay, I will invest for half of the World Cup or half of the IPL. So that was not something that was allowed, right? Question is that, do you want to go for the World Cup or not? Do you want to go for web ads or not? And so on, right? So I am saying that, okay, I will pick the variables x1, x2 to x5 on 0, 1 variables, indicating whether I want to invest in those schemes or not. Actually, there are 6 of them. And now I have this whole thing, right? So I know what do I have to maximize? I of course have to maximize. If x1 is 1, then I will reach 10 crore people. If x1 is 0, I will get it 0 people from in this set. So similarly, if x2 is 1, I will get 15 crore. If x2 is 0, I will get 0 crore. So the total, what I want to maximize is summation of, so I'm basically 10 of x1 plus 15 x2 plus 0.5 x3 and so on and so forth. And the constraints are, of course, again, see, this is a 0, 1. So like if I invest in the World Cup, I spend 2.5 crore, 3.5 crore. If I don't invest in the World Cup, I don't spend anything in this direction, right? The total amount of money spent is with 3.5 into x1, 5.2 into x2, and so on and so forth. And this sum should be less than 6 crore. Similarly, for the people. So,
Sir, here I can use that that is exactly equal to 6 because budget is 6, so we can optimize it by using the 6 crore. Like I can use obviously less equal to 6, but
you can use less equal to 6. So how are you suggesting?
I'm suggesting that it should be equal to 6 because 6 crore is for like budget. So like it will be optimized, right? If I use
No,
most
not
of it.
necessarily. See, again, you cannot crank it up, right? In fact, there is no reason why you can always go for a, like, for example, here, I mean, let's see.
Because here profit is not in like crore or some, not in monetary value. Profit is like expected reach.
Right,
So-
but I want to
Yeah.
kind of say that the cost that I spend, this money that I spend is at most 6 crore, right? You were
At
saying,
most, I got it, but
yeah, I mean, like, there is no way I can, okay, of course, you can say sell 6 crore by giving some extra amount of money to IPL or something, but that is not the point, right? Right, so you want to maximize this while you have this condition. This is less than 6, and there should be another condition, and I have missed it.
No. Probably she would like to say that, like, why can't we use a plane equal to 6 instead of less than or equal to 6? Let us try to see whether it has a solution or not. Like that is
Okay.
also a valid equation, valid
It
condition.
is a
right?
valid equation, but my
Yeah.
job is not to see whether there is an equal to 6 or not, right?
Yeah,
I'm not
fine, but-
optimizing this thing. My job is to optimize this.
It's possible that without spending 6, we can meet the target.
So how do we decide the conditions according to the given problem? Like that might be an issue here.
Okay, why?
How
what-
do we decide the conditions?
What are
Yeah.
written there? You have a budget of 6. So total amount of money that you spent must be less than 6. Total
Okay,
number
less
of
than
people
equal,
that you need is less than equal to 10.
Okay, sir.
Right.
Okay, fine.
Yeah, for example, here, in fact, in this one, if I'm not wrong, what you might find is that you cannot spend 6 crore and get the optimum thing. Yeah, I mean, try to. So I think in this situation, if you put this to be exactly equal to 6 crore, then you will get a number, okay? But
Yeah.
there will no guarantee that that maximum value, that value that you will get, is the maximum.
Comparing two maximums, yeah, we can compare two maximums. I don't know.
I mean, it's
Doesn't
not
make
very
it
clear
clear.
whether that maximum will be the right maximum, right?
Yeah.
I mean, then the goal will be that, okay, I have to spend 6 crore. And under that condition, how many can I reach?
Yeah.
But the main point is that this is an inequality.
Right.
So it can be equal to 6.
It can be equal to 6. But
Yes,
if you put that it is equal to 6, then you're limiting the set of possibilities.
That
here-
way, then we can say that I have 10 people. Why don't I use all 10 people?
Exactly.
I mean, same thing.
Exactly.
Ah,
In that case, there
same.
are 10 people, why don't I use all the 10? Yeah. So you should always remember what is it that you want to. I mean, I'm not even trying to use my brain here, honestly speaking. I'm just reducing that problem to a linear programming formulation. That's it. So I'm not trying to even say that, okay, since I have 6 crore, I better optimize and try to solve the 6 crore or use 6 crore or something like that. No, nothing like that. I'm just trying to reduce the problem.
Okay, but sir, like for solving this equation, anyhow we have to like in the condition we have to use like plus x7 equal to 6. We have to do like that. Like I did it in BSc, so anyhow we have to do it equal to 6.
Again, if you put a plus x7 equals to 6, that is good, but then that x7 doesn't have any constraint.
Yeah, x7 doesn't have any constraint. Yeah,
Yeah, so that is important.
greater than equal to 0. That is
Yeah,
only the
greater than
constraint.
equal to 0. That is very important, that it doesn't have any constraint. Okay. There's some racket out here.
And less than or equal to 6 also has to be there, right? X7.
Yeah, less than equal to 6, but otherwise
Again, we have to eradicate that X7.
Again, I'm saying, don't think of how to solve the LP. I think
Yeah,
you're
yeah,
getting confused over there.
Yeah, fine.
Okay.
Fine.
Don't even try to think how to solve the LP. The goal is to just write it in terms of LP. Okay. Okay, so this is the condition. And one thing that nobody had pointed out is that there's an issue which is more delicate. That the x1, x2,
Sir, solving. Yes.
sorry?
Yes, sir. By solving this, we will get a real number by L.
Right. So if I want to insist that this is a 0 and 1 and not just any real number, so this is not a proper LP. Okay. In fact, if you insist, if you give a general LP, okay, and say that, okay, the variables can take value 0 or 1 or anything called the integers, just integer value, then that is called an integer linear program. And this problem becomes hard. Now, what does it become hard? I will come to that later in the maybe next week or something. But basically it says that we don't expect to find a polytime algorithm. Okay, so there is no packages that can handle this thing. Okay, there are no packages that can handle this issue. How can I optimize this thing? Because the packages are slow. Actually, I should rectify myself. There are packages, but they are not polytime. There are packages, they output the correct value, but they are not very fast. So either you have to use those packages, which is something that is used a lot nowadays. Okay. But under the hope that somehow for this particular instance of the problem, the algorithm, the package will solve it quickly. Or you have to come up with a different idea. Okay. So, okay, so now, so is this clear? What's the issue here? So basic thing is that if you reduce a problem to a linear program where the variables are allowed to be reals, then that is a polytime algorithm. They're nice packages, applied, done. If the variables have to take integer values or something like just 0 and 1 value kind of stuff like that, in such situation, the problem is not a polytime algorithm. So there are solvers. They are called the ILP solvers, integer linear programming solvers, but they doesn't necessarily solve very quickly. Of course, so nowadays in the industry, it is very common to use these solvers. We will see some more of that in the next couple of classes. There are very nice heuristic algorithms that manages to solve these problems very nicely. Although it is known that these problems are hard, you don't expect it to solve in polynomial time, but for most what is called a real life application, okay, this solver manages to solve it quickly. So this is where the issue of this hardness comes in. Okay, so when we say that this ILP is hard, it means that the worst case running time is hard, meaning there exists a problem of the ILP and a special instance of the ILP where any algorithm will take more than polytime. But that doesn't mean that for spatial problems or spatial instances of various problems, it cannot be solved quickly. Okay, so this is something very important concept that you should kind of always remember, that if you can reduce to a polytime algorithm, great. If you reduce to polytime, I mean an LP, wonderful, you're done. But if you reduce to not an LP but an ILP, then you can use some solvers, but they are not necessary, they're not fast in the worst case, but in many instances they can give you a very quick answer. Okay, now what happens if they don't give you a very good answer? Okay, and there are instances where that happens. Okay, and in that case you have to come up with a different style of solving these problems. So now let me give you a very quick idea about how one can hope to try to solve this problem. So this is something, whatever I'm going to say in the next 3-4 slides, if you are not interested, you can forget it. Okay, this will not be a part of your course. So basic idea is that what we call as the relaxation of the integer linear land programming. So here you have this problem, right, where the variables are supposed to take values 0 and 1. So instead of doing that, I said that, okay, I will not take this line, and instead I will insist that I will just say that these variables are values between 0 and 1. That's it. Okay. Now, what's the issue? See, of course, I can now solve this problem. This problem becomes an LP. I can solve it. But this answer or the optimization might give us things like, okay, so you should go and invest points, you should focus on 0.7 of the World Cup and 0.3 of the IPL or something like that. Now, those things don't make any sense, right? That doesn't make any sense because we are not expected to output, invest in 0.5 of 7 of the World Cup. There is no, the World Cup doesn't have give us that liberty. So how do I then solve it? Okay. So, but what we do is that we first let us solve it. Okay. This LP, where we are saying that, okay, these variables are real numbers. And say I get a solution. Say x1 equals to p1, x2 equals to p2, and so on and so forth, be a solution. So what does x1 equals to 1 mean? So if x1 equals to p1 means x1 equals to the 0.8, means it is saying that, okay, you invest into 0.8 of the World Cup, right? X2 equals to 0.3, meaning you invest in 0.3 of the IPL, and so on and so forth. Again, doesn't make much sense. I have to decide, should I invest in the World Cup or not? Should I invest in the IPL or not? Right? So somehow, by looking at this set of PIs, I need to come up with 0-1 assignment of exercise. Right? I have managed to get an assignment of the exercise, but they're not 0-1. From these real assignments, I need to come up with a 0-1 assignments of the exercise. Okay. So here is a trick that we can do. Every PI is a value between 0 and 1, and you assign xi equal 1 with probability PI and 0 otherwise. See, there are some lots of issues that can happen here. Like, for example, what happens if the actual value of all the xi's were 0.8, right? Or 0.9, something like that. So that means with 0.9 probability, I am putting all the values as 1. So in some sense, we are saying that, oh, okay, we go and invest in all of them. And that might not be a feasible solution. So there is no guarantee that this assignment of exercise is a feasible solution. Okay.
Sir,
and
can you please
yeah,
repeat the last sentence?
Right. So see, this was a feasible solution, right? X1 equals to 1, P1, X2 equals to P2, and so on was a feasible solution. Feasible solution meaning it satisfied all the constraints.
Yes.
But now if I make X1 equals to 1 with some particular probability and 0 otherwise, right? It might be that it will make all the exercise as 1. Right? And that assignment might not be, there's no guarantee that that assignment is a feasible solution. That assignment will satisfy all the constraints. So it might be that, oh, okay, I have found out an assignment, but that assignment is spending too much money or requiring too much people. Okay. So, okay, so I started with trying to solve a problem. I did an ILP, then relaxed it to LP, solved the LP, used the LP solution to obtain an assignment, but now that assignment might not be a valid assignment. Now, there are certain issues that can be proved. That what you can prove is that, okay, although we cannot say it with high probability, we cannot say what happens, but you can see that the expectation, and I will not go into these details at all, the way in which I have assigned it, on expectation, these values are satisfied. So expected amount of money that I spend will be less than 6. Expected amount of people that I need will be less than 10, and so on. Okay. So while that doesn't give me a algorithm, a proper assignment with perfectly, but that kind of gives us some nice structure. Okay, it says that okay, on expectation you are fine. Okay, in fact, the amount of return that you can expect or the number of viewership will also be something similar to what it was earlier. And this is one way. So I didn't say what to do, but this is a way. So I mean, after this whole statement, this is obvious whatever has been written here. But after that, from that, you can try to prove something from there nicely. Okay, that okay, after doing all of these things with high probability, I will be fine. Or with high probability, I will give you an assignment that is that does a very good job, that almost optimizes it. Okay, and such statements, this part of this whole area of work is what is known as the approximation algorithms. Okay, again, this is the introduction to a different topic. There are whole advanced algorithms courses that are given, and a big chunk of it is the approximation algorithm. And this is a crucial area where you can go from here, that how to solve an ILP solution algorithm. Okay, and basic idea is I have ILP, you reduce it to LP, solve it in polytime, use that solution to obtain a feasible solution of the whole thing. Okay, so anyway, so I am running out of time today. So what I wanted to do is that I wanted to come up, give you certain set of problems, and I wanted to show you the power of linear programming and how that helps in obtaining or solving many equations, many problems, right? We looked into the linear programming and we looked into ILP. Crucial thing is that if you can reduce a problem into LP, then done. You can use a solver and whatever stuff to solve it quickly. If you reduce it in ILP, then you can also use a solver, but there's no guarantee that it will solve quickly. And if it doesn't solve quickly, then you might have to come up with some other ideas. And approximation algorithm is a way to go about it. So there are lots of issues about linear programming, and I don't want to go into that. Okay, so many optimization problems can be written as an LP problem and can be solved. The whole subject of linear programming is a very beautiful subject with lots and lots of interesting things there. It's a mathematically outstandingly beautiful and algorithmically very challenging and very exciting area. Of course, the modern day optimization has moved quite far, and we don't do linear programming. We do what is called a convex optimization and so on and so forth, which are much more delicate objects to handle. But basic idea is okay. So you kind of take any optimization problems, you can solve it, reduce it to some standard structure and solve those standard structures. Okay,
Sir?
so yeah.
What about linear integer programming when the coefficients are also integers?
That doesn't help.
Because like every time any linear combination will give us integers, then we can check for GCD
No,
computations, right?
that doesn't help. No. If you are only guaranteed that all the coefficients are integers, that doesn't really help. No.
Okay.
Yeah. But there are problems which can be written as an integer linear program, but still they can be solved in polynomial time. Okay, it is not necessary that all problems that can be written as an ILP cannot be solved in polynomial time. Okay, it says that in general I don't have a solution for any arbitrary ILP in polynomial time, but for certain special case kind of functions or kind of problems, we might be able to solve it in linear time. So I will stop today and I leave you guys with these 3 problems. you have seen those 3 problems. I want you guys to go back, and I will upload the slides and this talk. Please go and try to model these problems using linear programming.
Sir,
or
problem number
intelligent
4.
programming. Yeah.
Problem number 4 doesn't have any data.
What do you mean it doesn't have data?
I mean, there are only n stations, and there are only
Yeah, there are n stations. I mean, the stations are kind of some points, right? You can think of them as a grid.
I can understand the constraints here.
You don't understand the constraints here?
No,
There is no constraint. What do you mean?
like there are n station.
There's n
So-
stations. You have been given n stations. Okay.
Given n stations. Yes.
Okay, n stations, and you have a set of locations where there is a tower, right? And of course, you know that it's in the city. There is some distance between them. That's also given to you, right? So think of it. In Calcutta, if somebody says that you have to, someone gives you the map and says that put some pins in various locations in Calcutta, says that these are the important locations which I want very good for 5G, and also another colored pins that are given to you says that, okay, these are the places where I have towers. Now, some of the towers have to be upgraded. How do I do it? So your input is that map and the set of pins. Is it clear? Hello?
Okay, sir, I'll think about it.
Okay, think about it. Okay, so I want you guys to go back and try to solve all the 3 problems. And it is very important, because not only will that be useful for the other things, but we will start from the problem number 3 in the next class. So please go about it, and we will meet on Thursday to discuss more of, not of linear programming. We will go to something else after that. Yeah, okay. So any questions? I mean, we can end the class now, but if there is questions,
Hello,
I will
sir.
be able to handle. Yeah.
Can we extend the last date of submission of assignment 4? I mean, there are too many assignments this week.
When is the last date?
25th.
25th. 25th is next Tuesday, right? 25th is a Friday.
Yes.
Okay, you can extend it to the Monday, but there will be another assignment coming on Monday only.
Okay, sir. So last date is 28th.
Yeah, sure.
Okay, sir.
Any questions related to this, whatever has been discussed in this class now?
Sir, for solving linear integer programming,
Hmm.
what if we solve it like for real numbers only,
Hmm.
and then we round those numbers off to form the integers?
I mean, that is exactly what we kind of did here. We did it a randomized rounding. What you are talking about is a deterministic rounding.
Acha.
Okay. It sometimes works, sometimes doesn't work.
Okay.
Okay. So it depends upon the problem. And there are not one way of rounding, there are multiple different ways of rounding that you can do. So there's a whole area which does that. I mean, question is that whatever you are going to get is not necessarily so there are 2 ways that you can mess up. One is that the solution that you get might not satisfy the constraints. And the
Yes.
other one is that the solution that you get might satisfy the constraints, but the optimum value, you don't know how far is it from the actual, I mean, your output is how, you don't know how far is it from the optimum value. Okay. So it
Okay.
depends upon which problem you are ready to sacrifice what and so on. It matters. Okay. Yeah. So then I must say that, okay, if you guys are interested in this kind of objects, then there is this another way of doing it, which is called, every linear program has a dual of itself. It's called the dual program. So a maximization problem is same as a minimization problem. So I mean, for every maximization problem, there is a minimization problem, which kind of is the dual of each other. Okay, and this is called the primal dual theorem, which says that the LP world, these two maximum and minimum values are same. So using the dual technique also. So if you want to solve the LP in the primal, the same as solving the LP in the dual. But if you try to solve the ILP, then that's a bit, you have to be a bit tricky. So sometimes what is done is that you solve the problem in the dual and then round those values to get an understanding of the primal solution. Again, if you do not understand it, that's perfectly fine. I mean, these are things that I'm just kind of trying to plugging in for other courses almost. But this is a beautiful area of work. If you are interested, please take the optimization courses. Okay.
Sir.
Yeah.
Sir, in your last class, you had talked about a coding question in assignment 4, but sir, in assignment 4, no question says that it requires a code. So, sir, can you please
I think the last one, if I'm not wrong.
Is it the last one, sir? Because it was not specified in the assignment that it requires a code.
Yeah, the last one, it requires a code.
Okay.
Yes, sir, for the last one, can you give some hint? I mean,
What's this?
last question number 5.
For this one?
No, sir, in the assignment.
In the assignment? No, I cannot give you any hint.
Okay.
I mean, particularly if you need hints and all, you should come and ask it in the tutorials and all this kind of stuff. Did you come to the tutorials?
Yes, last day I was there.
That's where you came?
Yes, sir.
Okay, and you asked these questions there?
No, I mean, I solved till the 4th. After that, I just
No.
I was reading about the question 5 last day.
Yeah.
And for problem 5, we have to write the code. Right?
Yeah. That's
okay, sir.
Okay, so if you don't have any other questions, I will stop the class now. We'll meet on Thursday.
Hello, sir.
Yeah.
Like, what do you mean by integer linear programming is hard in terms of number of solution space, or I mean size of the solution space, or what is it exactly? So
I'm using a terminology.
Yeah.
Okay. This terminology I will going to explain only in the next one.
Okay.
Integer linear programming is NP complete.
Okay.
Okay.
But in terms of NP complete is fine, but in terms of what the inputs should be
Exactly. I am not telling anything. With NP complete, if you knew that, if you know what is NP complete, then you will find. Else you will understand next class in the next week.
Okay, fine.
Yeah, so we are kind of moving towards the end of the algorithm. So it is like more like trying to understand which is hard, which is easy. What do I mean by a hard? What do I mean by easy? And lot of such kind of questions. And this is exactly what we will be answering in the next whatever lectures that we have. 5 more lectures. Okay. Good. Thanks.